it's hard to distinguish between two classical music artists like Bach and Mozart because neither of them are very funky.
In your
maybe
opinion.
they consider them, hey, they might have considered themselves very funky at the time.
Welcome to Nerd Out at Spotify, where we bring you behind the curtain of the world's most popular audio streaming subscription service. Machine learning, open source, clouds, tabs versus spaces. We'll talk to Spotify engineers about interesting tech issues, big and small. I'm Dave Zolotusky, principal engineer at Spotify. Today, we're going to talk about a really fundamental problem with music recommendations. How do you get a machine to find a song that's similar to another song? How do you describe the characteristics that it should look for? And then, does it just compare each track to every other track one by one until it finds the closest matches? When you have a catalog of 100 million different tracks, like we do at Spotify, that would take a really long time. For these kinds of problems, we use a technique known as nearest neighbor search. And that brings us to the subject of this episode. This past summer, we started using a brand new library for nearest neighbor search, replacing the one we'd been using since 2013. We call the new search library Voyager. You give it some input, and it explores the vast reaches of our datasets to quickly find close matches. It will go where no search has gone before. Today, we're talking to two of the engineers who built Voyager at Spotify, and also open sourced it for anyone else to use. Mark Coe, and, returning to the show, Peter Sobot. All right, let's just start by getting to know you guys, and I'll start with Mark. Tell me about yourself. What do you do at Spotify? How long have you been here?
Sure. Yeah. So my name is Mark Coe. I've been at Spotify for a little over 7 years, and I'm a senior machine learning engineer, and I work on the core music recommendation systems at Spotify that power things like Discover Weekly, the search page, your home screen, etc. And my business card actually says that I'm an expert data swizzler because I come from more of a backend / data engineering background and kind of moved into the machine learning space. So what I used to say is that my job is all about taking data from over here, swizzling it around, and then putting it over here.
I got you. That sounds super interesting. And we had Peter on before, but Peter, you want to say a few words about some of the awesome things that you do here?
Sure. Great to be back in the podcast. Thanks, Dave. My name is Peter Sobot. I'm a staff machine learning engineer, and I focus on machine learning for audio processing at Spotify. So I do a lot of machine learning stuff, a lot of infrastructure work, a lot of C++ for audio processing, and all the glue to make all of that work together. And I actually used to be on Mark's team, which is where we got to work on a lot of this cool stuff together.
We're here because we want to talk about some cool stuff you guys have done lately with something called Voyager. What is Voyager? Why is it cool? Why should we be talking about it?
Voyager is a software package that we've just open sourced at Spotify for doing efficient nearest neighbor search in Python and in Java. So Voyager is a package that allows us to power a lot of the features that we use at Spotify, and now it's available to the rest of the world.
Why does this matter? Why do we even need any of these things? You said nearest neighbor search. You mentioned that it's all open source. Just explain to me why we did that.
Because open source is great, but why do we need nearest neighbors to begin with? Well, for this, actually, I might punt over to Mark, because Mark's got a great way of explaining this that I enjoy.
Sure. So when you're doing machine learning, and just when you're trying to make, for instance, music recommendations, you often are faced with the problem of what's called candidate generation. And that's the idea of you have something, maybe that's a piece of music or an item, and what you want to do is find similar things to that item. So for instance, if you're shopping on the web and you have a chair that you're looking at, maybe you want to find other chairs that are similar amongst the whole internet, right? There's a lot of products out there. So how can you find other chairs that are similar in a fast and efficient way?
So for the visual learners, can you give us a more visual walkthrough of how this thing works?
We have a pretty good example that kind of lays the groundwork for the rest of this. When you think about locations on a map, right, you have the longitude and latitude of locations. And that's a good way to describe geographically where something is in the world. And so where we see the nearest neighbors problem in something like this is, let's say that I posed you with a task, and that task was to open up the Maps app on your phone and find me restaurants that are nearby the Empire State Building. But I want you to do it without using the search bar, right? So if you open the Maps app, and let's say that you live in Stockholm, right? The map app is probably going to open up. It's going to show you your little corner of Vasastan or something like that, wherever you live in Stockholm. And it would be crazy if you just scrolled over on the map until you kind of happened across the Empire State Building, right? That would take forever. So instead, the first thing that you're probably going to do is zoom all the way out, right? So that you get a kind of overview of the whole world. And then you would probably rotate the globe a little bit until you see, well, I know the Empire State Building is in America or the United States. And so you scroll over until you see the United States. And then the next thing you're probably going to do is say, well, I know that Empire State Building is in New York, and New York is on the eastern side of the United States. So you zoom in there. Then you see a bunch of states. Well, I know it's in New York. You find New York amongst those states and you zoom in a little bit more. And then you keep zooming in more and more until you find New York City. And maybe if you know that the Empire State Building is in Midtown in New York City, you zoom into where you think it approximately is and you see a bunch of restaurants around that area. And that is effectively how this Voyager thing is working when we are asking it to find nearest neighbors to a point.
So I assume, like we're talking about Voyager now, it's a fairly new thing, but we've been doing a bunch of these sorts of things for a while. What did we do before we had Voyager?
That's a great question. Spotify has been using nearest neighbor search for more than 10 years now. We were one of the pioneers in the area, actually. Former Spotify put together a package called Annoy, which is very popular in the data science world. It actually stands for Approximate Nearest Neighbors. Oh, yeah. That's literally what Annoy stands for. And it's been really, really foundational. It's helped us at Spotify. It's helped a bunch of people outside of Spotify. But it's more than 10 years old at this point. Rather than try to make small incremental upgrades to the algorithm and see how far we can push that 10-year-old package, we decided to make a big step change upgrade and learn from the community and take in the most recent updates to build Voyager.
Tell me a little bit more about that. First of all, you kind of approached that as if it was clear that we needed Annoy to be better. Like you were talking about incremental upgrades versus like a whole different thing. Why did we even think we needed a better Annoy?
Annoy does really well for searching through vectors that are fairly small. So 10 years ago, it was common to search through vectors that had maybe 40 or 80 or 100 dimensions in them. So not that large. But in the past 10 years or so, people have expanded what's reasonable, let's say. Now, it's not uncommon for someone to build a machine learning model that outputs embeddings or vectors that are thousands of dimensions in size, or 1,000 or more, or sometimes many thousands. And with that size of embedding, Annoy doesn't really hold up as well, or it becomes much, much slower to find useful results. And so rather than tell people, oh, we don't really have the technology to allow us to search those new fancy machine learning embeddings, we decided, well, let's upgrade the packages that we use so that instead we can support use cases like that, use more advanced machine learning techniques, and hopefully have better quality music recommendations.
I gotcha. So that makes sense. And that does sound like a pretty significant change. Like you go to multiple orders of magnitude of scale, and I can see how you wouldn't think, let's just tweak this algorithm real quick and it'll work. So then tell me a little bit about the differences between Annoy and Voyager. Like, how is there this magical thing that exists elsewhere that's just orders of magnitude faster?
So Annoy and Voyager are built on two completely different techniques for doing nearest neighbor search. Annoy uses what I think is called a tree partitioning algorithm, essentially a fairly simple algorithm that was invented around the time that Annoy came about. And Voyager is using a new technique called HNSW, which is a very easy to mispronounce acronym that stands for Hierarchical Navigable Small Worlds. Very fancy name for a fairly simple concept that we can talk about and get into detail about. This was published about 3 or 4 years ago, and it's been fairly popular since then. It's in a number of different packages that you'll find online that are open source. It powers a number of database products and things like that. And it has much, much higher quality than the old Annoy approach did. For the same query speed, we can get roughly 10 times higher quality results, or we can get 10 times faster speed for the same quality of results that we used to get with Annoy. So it's pretty much, that order of magnitude improvement there. And we can also search through much longer embeddings and things like that.
That's pretty amazing. I guess this is a thing that I assume was invented after Annoy, or was it just a whole different thing that Annoy didn't, for whatever reason, we didn't use it in Annoy like a decade ago?
Yeah, it was invented well after Annoy. I think the paper was published in April 2020, if I remember correctly. And Annoy came out in, 2013, maybe around then. So yeah, definitely just the academic community and the research community advanced the state of the art since then. And Annoy was not really updated in that time because it's really hard to update a really popular software package. Once you have a bunch of users, like changing the core algorithm that would be a pretty difficult feat.
Yep. Like you can change it, but if you're going to completely gut it and gut its most important piece, I'm sure there are people that will be psyched that it's so much faster and people that will say, well, actually, I depended on a bunch of things from that algorithm. So even just comparing these kind of already fairly advanced nearest neighbor algorithms to just something we're all familiar with, like, I don't know, in school, we'd have learned about linear search or binary search or, I don't know, bucket sorting or whatever, like a bunch of different simple CS algorithms that we could probably also use for something like finding restaurants on the Empire State Building. But I assume because you use things like Annoy and Voyager, these things are multiple orders of magnitude better than like CS, I don't know, 201 level algorithms.
Yeah, so those CS level 201 algorithms are extremely useful for certain types of data, right? There's a reason we still use binary search all over the place and things like that. But as you have more and more dimensions to your data, it gets harder to use those simpler algorithms in an effective way. So to go back to Mark's example of looking for points on a map or looking for the Empire State Building, if you were to do binary search just to find the Empire State Building on the globe, you have two dimensions. So you could binary search in the latitude direction and the longitude direction, and that would narrow you down in 2 steps. But if you had more than 2 dimensions, if you had 40 dimensions or 80 dimensions, you'd have to do that 40 or 80 times. If you had thousands of dimensions, now suddenly we're getting much, much, much slower just to use that old simple algorithm. So these nearest neighbor search techniques allow us to search through much higher dimensionality of embeddings, so 80 or 1,000 dimensions or something like that, by being approximate. So they don't give you the right answer every single time. They give you probably the right answer every single time. And they do that with a number of techniques, but that approximate nature allows them to operate much faster, operate probably hundreds of thousands of times faster at scale than actually doing binary search or doing linear search through all the possible options.
So if you just had one dimension, let's say it was just the longitude, right? If you wanted to find how close something was just by longitude, it's pretty easy, right? You order things by their longitude and then you can apply binary search. But as soon as you add a second dimension, it becomes even less trivial than that, because even if you search the longitude and then the latitude, maybe one of those dimensions is more important than the other for how similar two things are, right? If something is all the way at the top of the Earth, then the difference between the latitude is probably always going to be different. So then you really care about just where that longitudinal difference is. And you could say the same for vice versa. And when you get into higher and higher dimensions, it becomes much harder to really visualize what a distance is. With a line graph, it's just the distance between A and B on that single dimension. With 2 dimensions, it's like, okay, I can think back to high school and remember my Pythagorean theorem, and that's how far 2 points are on a 2-dimensional space. But once you get into 3 dimensions, it becomes even hard to just think about, okay, how close are 2 points? Once you go beyond 3 dimensions, we just can't actually even visualize that in our mind because we live in a 3-dimensional world.
Yep.
There's a famous machine learning professor, Jeff Hinton, who has a famous quote saying that if you try to visualize a higher dimensional space, visualizing 15 dimensions in your head, just say the word 15 and close your eyes. You won't get it, but it's the closest you can get.
Sounds reasonable. One thing I want to go back to is both of these things, or really nearest neighbor as a whole, but both Annoy and Voyager don't sound like kind of core audio things. Like I imagine there are, I'm going to say millions, but I don't know what the actual numbers are of use cases in the world. Why are either one of these things that Spotify built?
So we built Annoy 10-ish years ago because we had that need specifically for music recommendations, and it turned out to be extremely useful for us. So Annoy is one of the reasons Discover Weekly works so well, and many of the recommendations you get every day work so well. Voyager is kind of similar. We needed a major upgrades because we use similarity search all over the place at Spotify, and that powers not just recommendations, but many other small parts of the experience. These problems don't specifically apply just to audio, though. You're right. There's nothing about Annoy or Voyager that requires us to use music or use podcast data or anything like that for similarity search. It just so happens that recommending music gives us a lot of data points to search through. And if we have a lot of data to search through, we need an efficient algorithm to do so.
Yeah, that makes sense. And I think the angle I was more trying to figure out is, I think there are probably many other organizations, whether they're companies or universities or anything else, that also want a very good approximate nearest neighbor algorithm. Why didn't one of them build it? Or why didn't we use the one that one of them built?
There actually are a lot of competitors in the space for approximate nearest neighbor search. Annoy was one of the first, but since then, there are countless others that honestly, I don't even have a list of because there are dozens and dozens. When we open sourced Voyager recently, we're actually building on top of a well-established open source library called HNSW lib, which is actually the most common implementation of this HNSW technique that was in that paper I mentioned. And HNSW lib is great. It's widely used. It's already out there on GitHub. It's very nicely licensed and things like that. However, we wanted something that was a little bit more suited for our production infrastructure. We built Java bindings on top of it so that we can run that in our Java services and things like that. We totally revamped the Python bindings. We added a whole bunch of nice stuff that we really expect from our libraries and kind of just added a bunch of polish on top and then some new features as well. Other companies have, again, built systems just like this. There are entire startups that just do what are called vector databases nowadays. And those companies are powered mostly by nearest neighbor search, but then they add tons of additional features, things like being able to query with text or putting actually machine learning models into the vector database themselves. It gets very, very impressive and very complicated. But what we wanted from Voyager was a very simple library that we could embed in our existing software. No dependencies, nothing that we needed to maintain or operate, just a library that we import and run.
And there's a few examples of what Voyager does specifically that we really depend on, which is, for instance, you can generate this index that's useful for looking up nearest neighbors, and you can save that as one big file, which you can then ship around to a bunch of backend services. And it's a pretty compressed format. And once that's on backend services, you can use it to do all your nearest neighbors lookups, or you can bring that into a data pipeline. And maybe your backend services are written in Java, your data pipeline is written in Python, and maybe you have your core library in your application that is written in C++. And so Voyager is written so that it's all using the same kind of core code under the hood. And so you get the same behavior, whether or not you're calling this from Java or whether you're calling it a machine learning model or anything like that.
You talked about HNSW lib as a canonical implementation of HNSW. Why aren't we just using that? Why does Voyager even exist when HNSW lib does?
Yeah, so HNSW lib is very widely used and a very popular and very well-established library. Unfortunately, with that wide use, we also have a lot of existing code that uses that API and uses all of the quirks that have been built into that library over time. When we asked ourselves what we wanted from a new nearest neighbors library, one of the things was a very simple and very different API. And so there aren't really any easy ways to change an API that's so well established. And so we couldn't have made the changes we wanted to HNSW lib.
Yeah, and also with HNSW lib, when we tried to use it at Spotify scale, where we're talking about millions and millions of items with billions of users, we started to run into snags and we found some bugs within kind of the core code behind Voyager that we knew we could fix if we had free reign over changing it, but we couldn't just go in and change fundamental assumptions within the library. So we're we're going to build something new that solves our problems, but doesn't force everyone to change all of their assumptions that their systems make based on their usage of HNSW lib.
I gotcha. That makes sense. Because with Peter's answer, I was thinking, so we're just wrapping this other open source thing that we just depend on and use, but put a different API on top of. But with what you just added, Mark, it sounds like Voyager has some kind of fundamental differences. So it is a different code base. And then I guess before we move on, quickly touching on the open source part, of course, I don't know. Open source is cool, like we talked about, but is there value or reason why either one of these really needed to be open source, or is it just the teams that worked on these really believe in open source and wanted to open source them so that we could work with others?
It is a bit of both. I would say for Voyager, I mentioned before, we based Voyager on HNSW lib, which is already open source to begin with. If we based Voyager on HNSW lib, we felt like we wanted to give our contributions back to the community in some way, right? And show we've made these improvements. Unfortunately, we can't keep API compatibility with the original, but we can publish a new package next to it, and anybody who wants to use these new features can use our new package.
Yep, that makes a lot of sense. And then the last thing I want to ask before I jump in is, I know we talked about finding restaurants in Manhattan, but rumor has it Mark has an excellent analogy for what is nearest neighbor search that I believe revolves around finding ducks. I can't move on from what are these things without hearing Mark tell me about finding ducks.
Oh yeah, this was a hotly debated topic. So in order to visualize kind of in a more concrete and accurate way about how HNSW or Voyager is working under the hood to do nearest neighbor search, imagine that you kind of like how when we were talking about the map example, you started really zoomed out. You were at the country level, right? And then you zoomed in a little bit more, you're at the state level. You zoomed in a little bit more, you're at the city level. And then you're within city. And you get this concept of the world. And let's say we had 1 million pictures of items, it's hard to just brute force search a million items every time someone's like, yeah, find me a similar picture to this duck. And so how HNSW kind of approaches this is when you start in that really zoomed out picture, let's say we have a picture of a duck, we have a million other images, and we want to find other pictures of ducks that are similar to our duck. And so you start in that first layer. And let's say in that first layer, and when I mean layer, we kind of descend down, and that's the whole like you're zooming into the map concept. So you start really zoomed out and you have this picture of the duck. That first layer, when you're at like the country or the continent level, doesn't have any pictures of ducks, but maybe it has a picture of a chair, it has a picture of a mountain and a cityscape and a car. You have to look through and say, okay, well, which of the items in this layer is most similar to my duck? Maybe there's a picture of a bunny rabbit. And so you start at that picture of the bunny rabbit, and then you go down a layer deeper. And in that deeper layer, okay, now there's more pictures of animals present here. And since we're starting at the rabbit, we're going to be in this animal picture area of this space. And so you look around for the items that are close to the picture of the rabbit, and maybe you find a picture of a goose. And it's like, okay, well, this goose is a closer picture to my duck than the rabbit is. So let me move over to there. And then we're going to go down a deeper level, and you would keep searching in that previous level until you find something that's like, this is as close as I can find here by just looking around at things nearby over and over again until I find the closest thing. So then you go down, and now you've got a picture of, previously you were looking at a goose sitting on a lake, but maybe nearby in the lower level, there's pictures of a goose standing in some grass. So now you hone in on that area, but there's still no pictures of ducks in grass here. So you descend one level deeper, and you can have as many layers that get more and more dense as you want. But in this bottom layer, let's say that you have all of the pictures. And finally, you are close to a picture of a goose in grass, and you keep moving around through the nearest neighbors to that goose picture until you find pictures that are actually similar to your duck. And that's actually a little bit more accurate than like the pinching and zooming, because in this example, we're talking purely about images or one type of information. And that is more often what you're dealing with in the approximate nearest neighbors search. So you're not going to have continents and countries and cities and states all mixed with your restaurants. You would more likely have a big, massive combination of restaurants, maybe 15 million restaurants. And what you're actually finding is like, all right, we're starting really far out in the world. Maybe we're going to start at a restaurant in Africa, and we're going to keep moving geographically closer to restaurants that are close to the GPS coordinates of the Empire State Building until we eventually wind up in New York. But you're doing it all through these connections of restaurants rather than like thinking about it purely at kind of a more country and map representation.
Oh, I gotcha. Yeah. So it's all based on properties of restaurants.
Exactly. And we like to give this example that when you're trying to represent similarity between music, let's say that you wanted to represent music in a vector, which is effectively just a set of numbers, right? And so let's say that you, for every song on Spotify, knew how funky that song was, and you knew how danceable that song was. And when you look at that, right, you can think of it as an X and Y graph, and the danceability is on the X-axis and the funkiness is on the Y-axis. And maybe you have Mozart and Bach, right? They're not really very funky or danceable. So they're all the way in the lower left-hand corner. And then you've got something like, let's say, some electronic genre, EDM, maybe it's tech house. Tech house isn't very funky, but it's very danceable. So that's going to be pretty far over on the X-axis, but it's going to be pretty low on that Y-axis. And then you've got something like funk music, right? Which is both danceable and pretty funky usually. And so that's going to be more in kind of the upper right-hand corner of the graph. And that's not exactly high fidelity information, right? It's hard to distinguish between two classical music artists like Bach and Mozart because neither of them are very funky. And so instead what we do is we,
in your
maybe
opinion.
they consider the, yeah, hey, they might have considered themselves very funky at the time. They probably were. But in music, we need more information than just that. And so what we do is we utilize machine learning to figure out what these dimensions should be. And in that example, it was just 2 dimensions. But in reality, we need a lot more dimensions to represent music accurately so that you can distinguish between a funk artist and an electro-funk artist, for instance. And so that's where we use machine learning to figure out, well, what actually is similar if we don't really care specifically about what each of these dimensions mean.
I gotcha. So I think that's a really good way for me to visualize what vectors are. I think there were a couple of other things you talked about in how we use the thing at Spotify. You talked about, I think, embeddings a couple of times. Walk me through what embeddings are.
The term embeddings and vectors we use interchangeably because embeddings are generally represented as a vector, and a vector can just be any sort of combination of information, right? Maybe it's like a person's height and their birth date, which are two kind of like unchanging values, but those are not super granular. Embeddings are generally generated from a machine learning model. And what you do is you take a lot of information and learn some series of numbers or some series of dimensions that can represent some concept or item in those series of numbers in a way that accurately reflects the data that you train on. So, for example, in Spotify, we have billions of playlists that are created by users. And in these playlists, you can imagine that the Rolling Stones and the Beatles probably do appear pretty frequently together in playlists, but the Rolling Stones and Doja Cat, for instance, may not appear as often in playlists together. And so our embeddings that we use for music kind of capture that the more frequently two items appear together in playlists, the more similar that they probably are. And the less frequently that they appear in playlists together, they're probably a little bit more dissimilar. And so these embeddings, the dimensions don't really mean anything to us as humans, but a machine learning model might take these embeddings and realize, hey, if I'm trying to build a jazz classifier, maybe dimensions 2 and 3, if a value for a track is high in dimension 2 and low in dimension 3, that tends to be where our jazz tracks sit. And so a machine learning model can understand these embeddings in a way that our minds can't really wrap our head around.
Yep. So now that we've walked through these couple of fundamentals that I think you've mentioned a few times, I want to hear a bit about how we use this stuff at Spotify. Like, what are the features that we all kind of know and love that are really built on top of this technology?
One of the biggest things we use similarity search for at Spotify is recommendations. And specifically, we built Annoy originally for Discover Weekly, which is our weekly playlist of new tracks you haven't heard before. And Discover Weekly is basically a wrapper around similarity search. So Mark mentioned earlier that we can use similarity search and this embedding technique to find out how similar different musical tracks are to each other, right? So we end up with this space where tracks that are similar to each other are close to each other in the space. They have low distance between each other. And we have tracks that are not similar to each other very far away from each other in the space. We can extend this concept to also embed users' taste by understanding what kinds of tracks they listen to. And then we also have a vector or an embedding for each user. And then to do something like Discover Weekly, all we need to do is search in that space of all the tracks that we have and say which tracks in this space are closest to this user who wants to listen to something new. That'll give us tracks that the user may or may not have listened to before, but that are similar to that user's taste. Then for Discover Weekly, all we need to do is exclude anything they've actually heard before, and the remainder is tracks they're probably going to like, but that they haven't actually listened to before. And that's where Discover Weekly comes from, with a whole bunch of additional business logic on top. That's the gist of it.
Are there unexpected things at Spotify that are based on this that aren't in this same space?
So one unexpected use case for similarity search is actually audio deduplication. So you can imagine we have a lot of different tracks uploaded to Spotify by labels and artists and so on. And sometimes those tracks happen to be duplicates of others. A label might upload another copy of an album that they've already uploaded in the past, or a greatest hits compilation or something like that. What we want to do is understand if two tracks are actually the same under the hood. So we can use machine learning to create an embedding from the audio itself and then do nearest neighbor search to see, are there any other tracks already in our catalog that are pretty much identical to this track? And by using that method, we're able to very quickly deduplicate audio and say, oh, we have 10 different copies of this popular song. And so we can group them all together for our metadata purposes and if they show up in the client and things like that.
It also can help with fraud and stuff. You know, if you just were to download some popular music track off of YouTube or something like that, and then upload it to Spotify, that's something that we would catch very quickly using a similarity search approach, as Peter just mentioned.
Are all of our similar recommendations, like we talked about Discover Weekly, but then there's a bunch of other things, I don't know, like all the stuff on Home that recommends things to you. There's daily mixes that are Discover Weekly, but not. Is like all of that based on this thing? Or do we have similar recommendation features that are completely different under the hood?
I would say Probably the majority of the music recommendations that you see on Spotify are influenced by this in some way or another. When you look at something like an artist radio station, we can represent other entities within our track space. So we could represent the artist there and find similar tracks to that artist to potentially put on a radio station. But maybe we also know some artists that the source artist, so to say, has like collaborated with or has appeared together in news articles or something like that. And so maybe they should show up on the radio station as well. And that is probably not done via this nearest neighbors search. Instead, that's using some other metadata. But this nearest neighbors search allows us to identify similarity when there hasn't really been any explicit interaction between two entities before, right? So let's say we add a new track to the catalog and it's not playlisted with some other track, but we know by the audio that it actually is pretty similar. Then we might put those two tracks together in a playlist and see how they perform together. But, I would say it's more used in a lot of recommendation surfaces than it being the only thing that's behind those recommendation surfaces.
Yep. I imagine there's a ton of other use cases beyond the things we've already done, beyond music, for nearest neighbor at this kind of crazy new scale that Voyager opens up. Are there interesting future things we're looking into? I think because it's 2023, I have to say something about LLMs right now, etc.
You said the LLM word, so I have to jump in here. Voyager really doesn't care what kind of vectors or embeddings you put into it. It's designed to operate at any scale. But one common new use case for similarity search is to take the outputs, or really the intermediate layers of an LLM, just embeddings that come out of an LLM, and put those into a similarity search index and use that to index documents or whatever your application is trying to index. This is a very hot topic right now, and there are many tools that do this very effectively with lots of bells and whistles and make it easier to use LLMs plus similarity search together. LLM embeddings could totally be used in Voyager, and I think we've tried experiments just to see what the community is doing and make sure Voyager can work with that kind of data. But it's certainly designed to be a very simple tool, and LLM embeddings work best when they're used with a lot of other tools as well. So personally, I think Voyager would be a great building block to use to build an LLM-based system, but you'd have to add a lot on top.
So there is a world of opportunity there, but of course, it's not just spin up LLM, throw a Voyager at it, things are done. There's work in between.
Exactly.
Hey, thank you both. This has been a lot of fun and super interesting. Thanks for joining me.
Thanks
for having us.
What other things do you nerd out about?
I nerd out about quite a few things. I think my most recent large pioneering and effort was introducing a feature called Exclude from Your Taste Profile. I get very nerdy about sleep music. I am like a fervent sleep music listener, and I use it to fall asleep every night. And what I found was that my Spotify recommendations started to all become like this weird ambient classical piano, because when 30% of all my music listening is sleep music, and that is actually a real number, it's actually pretty common amongst people who listen to sleep music or focus music. It's like, okay, 30% of the music that I like is sleep music. So when we do this nearest neighbors search, for instance, you get a lot of sleep music. And so my Discover Weekly became Discover Sleeply, which I was not super thrilled about. And so Exclude from Your Taste Profile allows me to go in and take all of my playlists that I use for sleeping and flag them as excluded from my taste profile, so that I can listen to that music without fear that like my Discover Weekly is going to think that I only like ambient classical piano sounds. And so I definitely encourage people to go use it if they struggle with the same problem. I know it's really useful for parents and people who teach like workout classes and things like that. So that's one thing that I definitely nerd out about, is I love falling asleep.
Thanks for listening, and don't forget to hit the follow button so you don't miss an episode. If you have any questions or feedback, email us at nerdout@spotify.com. Nerdout at Spotify is produced by Spotify's Ted Vergakis and by Seaplane Armada, who wrote our Neighborly theme song. I'm Dave Zolotusky. Thanks for nerding out with us.